Okay, hello everyone. Thanks for coming to this discussion session. Firstly, we will go over two hardest problems from quiz 3. Then we will work out several problems related to computers. So let's get started with the first one. This one is the problem 1 from quiz 3, and we needed to prove the statement by induction. As we already know, there are 4 steps to do inductive proof. First is problem statement. The statement is that we want to prove P0 times AN is equal to P0. Then we need to show the first case, the base case, P1. From P1, the left-hand side is equal to P0 times A1. It is equal to, okay, so it is equal to P0 times P1 plus A0. This is by the definition of A1. Then it is equal to P0 times P1 plus P0. Because A0 is equal to P0. And then P0 times P0 plus P1. This is bicommutative. Then it is equal to P0. This is by absorption. Now we proved P1 is true. Oh, it is equal to the right-hand side. So P1 is true. Then we need to make an inductive hypothesis that is Pn minus 1 is true. That means P0 times An minus 1 is equal to Pn. And then we go to inductive steps. We need to show Pn is true, assuming Pn minus 1 is true. Pn is equal to P0 times An. And it is equal to P0 times Pn plus An minus 1. This is by the definition of An. And then we want to use this inductive hypothesis. So we want this one multiply P0. So we can do P0 is equal to P0 times P0. This is by here.
And then it looks like there's a few students in chat who want you to go back a little bit and can't quite follow.
Okay, the first part, can you also send the block problem? Oh, okay, this is the problem from the previous section. Yeah, we are, okay, so Elizabeth, do you want to go back to the base case? So what's the problem with the base case? Okay, maybe because we have the P0 is equal to Pn, I think there is no problem with this one. Okay. Okay, then we continue. Then we can take the Pn out with this one, and this is by associative. Then we can use distributive to plug P0 in, and it is equal to P0 times P0 times Pn plus P0 times An minus 1. This is by distributive. Now finally we get this one, and this one is the same with the left-hand side of the inductive hypothesis. So it is equal to P0 times P0 times Pn plus P0. This is by inductive hypothesis. And then we still need to swap the make P0 be ahead of that. This is by here. Finally, we got P0. This is by absorption. Okay, then we are done with this part. Any questions so far? So the hard part of this problem is that we want to use the inductive hypothesis, so we need a P0 besides An minus 1. So we need to use distributive to have this item. Okay, so there's a question, what's the result of TA concerns? Grades are not out yet. Yeah, we are trying to publish the grade this evening, and we will give how you lose points or how you get points in our comments, and maybe you can see the comments from TA when you get the result. Okay, let's go to the second problem. This is the problem 6 from quiz 3. And we needed to prove that two sets is equal. So if we want to prove two sets equal, we need to prove that they are the subsets of each other. So there are two parts for this proof. In part 1, we needed to show the intersection of A and B is a subset of C. So in each part, we can use element-wise proof. That means we can choose an element from the left-hand side. And then we know this element belongs to A, and it is also belongs to B. This is by the definition of intersection. And then because xy belongs to A, we know there exists an integer that x minus y is equal to 2m, because in set A, x minus y is divided by 2. And also it's because xy is an element of B, so we also have an integer that x minus 1 is equal to 3n. Okay, there is another question from John. I meant on the overall difficulty of the quiz, not the individual. So, to be honest, this quiz is quite difficult. So the average grade will be a little low, and the professor and the TAs has already known that, and I don't know if we have further adjustment for the grade or something like that. But all of us has a one chance that we can drop one of the quiz for the final grade. So because all of the students, most of students did not do well in this quiz. So don't be afraid, and okay, I hope you will feel good after you get the grade, and we will publish it this evening. Yeah. Okay, let's continue. So we have now x minus 1 is equal to 2m and x minus 1 is equal to 3m. So we have 2m is equal to 3m. That means by the definition of even integer, we know 3n is even. And therefore, n is even, since 3 is not divisible by 2. And we know 3n is, because 3n is even and 3 is not divisible by 2, so n must be divisible by 2. So we claim that n is even. Because n is even, so we have an integer such that n is equal to 2l. And then we have x minus 1 is equal to 3n, so it is equal to 3 times 2l, so it is equal to 6l, which means x minus y is x minus y is divisible by 6. So xy is an element of C. Okay, we show that we pick an element from intersection of A and B. Then this element is also divisible. Is also an element of C. So therefore, the intersection of A and B is the subset of C. Now let's go to part 2. Show C is a subset of the intersection of A and B. We still need to pick an element from the left-hand side. And by the definition of C, we have x minus y is equal to 6p, where p is an integer. And then we know because x minus y is equal to 6p, so x minus y is equal to times 3p, and is equal to 2, k. Well, k is equal to 3p, and k is an integer. This is by the closure property of integer. So we have x, so x minus y is divisible by 2. So xy is also an element of A. Similarly, we also know x minus y can also be equal to 3 times 2p. It is equal to 3q. Well, q is equal to 2p, and q is an integer. It is also by the closure properties of integer. And then we know x minus y is divisible by 3. So xy is an element of B. That means xy is an element of A intersect B. Thus C is a subset of the intersection of A and B. So we need to make a final conclusion from part 1 and part 2. We show the intersection of A and B is a subset of C, and C is a subset of the intersection of A and B. Therefore, the intersection of A and B is equal to C. That's all. So, any question about this problem? Okay, we will just go over these 2 problems from quiz 3. If you have any other question about quiz 3, please go to our TA's office hour, and we will not publish the solutions on the canvas, so you need to go to the TA office hour individually. Okay, if you have no question about these 2 problems, we will go to the problems about combinatorics. Let's get started with the first one. So I will give you 2 minutes to think about it, and then we will work on it together. And if you're done with that, you can type your solutions in the chat windows, and we will discuss it with it 2 minutes later. Yes, there may be a bonus assignment that after the assignment 8, but I don't know when the assignment was published, but I'm sure that there will be a bonus assignment. Sorry, but we don't want to make our quiz longer because some students may have other classes and they maybe have not 2 hours windows for the quiz. So this problem we have discussed in our TA group meeting, and the professors will not have a longer time for the future quiz. Okay, there is a binary sequence. So a binary sequence is a sequence of digital integer that consists of 0 or 1. For example, a binary sequence of next 5 can be 1, 0, 1, 1, 0, and something like that. And if you finish your answer, you can type it in the windows for problem A. Okay, we have answers from Peters and another answer from Parker. So I need to make an emphasis that we have that this sequence should have exactly 3 ones. So we need 3 1 in the sequence. So this one is okay, but 1 1 0 1 1, this one is not okay because we have 4 ones in this sequence. Okay, your answer is right, Pepper. So let's get started. Firstly, we need to decide the possible lengths which satisfy this requirement. Since we need the sequences which has exactly 3 ones, so the shortest list should have 3 digits. And also 4 digits and 5 digits should also be taken into consideration. So for the length 3 sequence, we have 3 positions to put 3 ones in. So it is 3 to 3. And this is 4 to 3 and 5 to 3. So the total number is the sum of 3 of them. And it is equal to 1 plus 4 plus 10. It is 15. All right. Then how about problem B? Yeah. Okay, similarly, we have 6 positions to put 1 in, and we need to put 3 in 6 positions, so it is 6 to 3, and it is also 15. And as you see, the result for problem A is equal to the result of problem B. So why do these 2 questions have the same answer? Actually, there is a theorem states that so there is a theorem that is on page 408, exercise 42. That is CK plus CK plus 1 plus CNK is equal to. So you can find this theorem from our textbook, and if you want to prove it, you can prove it by induction. And if we use it in this problem, we can let k equal to 3 and n is equal to 5. Then we have 3 to 3 plus 4 to 3 plus 5 to 3 is equal to is equal to 6 to 4. So this statement can be proved by induction, but now we want to, let's try to get an intuitive explanation for it. Okay, James, can you answer the questions for the quiz on the chat? Okay, then let's explain why problem A and B have the same result in a more intuitive ways. Then firstly we can build particle triangles. These triangles is also can be found in page 403. And this triangle is simply a table for the value of n choose k in the shape of triangle. And the 1 plus 1 is equal to 2. And then 1 plus 2 is equal to 3. 2 plus 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 13, 20, 15, 6. So I just give the 1, 2, 3, 4, 5, 6. I just give the first 7 rows of the particles triangles. Then we need to show how to use it to explain this problem. And for these triangles, just to recall the definitions of the triangles, so we refer to the row and entry number starting with 0. That is, the top row, this row is row 0. And the leftmost entry of each row is entry 0. Using this definition, we see that entry k in N is the value of N choose k. Taking this value as an example, we see it is in 0, 1, 2, 3, 4, 5. So it is in row 5. And the entry of it is 0, 1, 2, 3. Entry is 3. So this number is corresponding to 5 choose 3. And if we verify it that we found 5 choose 3 is equal to 10. Now let's look at all the entry 3 item. And this one is the row 3, entry 3. So it's 3 choose 3. And this one is 1, 2, 3, 4. So it's row 4, entry 3. So this item is 4 choose 3. And so on and so forth. We have already know this item is 5 choose 3. And this item is row 6, entry 4. So it is 6 choose 4. Then because the constructions of these triangles, we know 55, which is 6 choose 4, is equal to 10 plus 5. Well, 10 is 5 choose 3. And 5 is equal to 4 plus 1. Well, 4 is 4 choose 3. And 1 is 3 choose 3. So we now have 6 choose 4 is equal to 5 choose 3 plus 4 choose 3 plus 3 choose 3. So this is an intuitive explanation of this problem. Also, you can also use proof by induction to solve this problem. Any question about this problem? Okay, then let's go to the next one. And this one is an easier one, so I will just give you 1 minute to think about it, and then please type your answers in the chat window. So we need two values in this problem. Yeah, just a reminder, the bad problem is that n plus r minus 1 choose n, where n is the size of the set. Okay. R is the size of the set, and n is the length of the unordered list. So because we want two winners, so the length of the unordered list can be 2. And the set is A, B, C, D. That means we can be, the answer can be AA, AB, DD, and something like that. So it is C. So we know the size of the set is equal to size of the set is equal to 4, and the length of the order list is equal to 2. So it is equal to plus 4 minus 1. It is equal to 5 choose 2. So I use this one directly from the chat window, but normally we will use n as the length of use n as the size of a set and r as the unordered list. So this may cause some confusion. So this is a problem that we can use the back problem directly. Now let's go to a harder one. Okay, let's go to this one first. And still, this is a problem with permutation because the order matters. So please type your answers in the chat windows. Yes, half of the cards instead are red. So we have totally we have 26 cards that are red. Yes, correct. And okay, because we are at how many lines, not the possibility, so you do not need to divide it by the total number. So the answer should be P is 26 permute 5. Because the order matters, so we need to use the permutation. And it is equal to 26 times 25 times 24 times 26 times 22. Okay, now let's go to problem B. At least one red card. Okay, Elizabeth said 22 to the power of 5 minus P, 26, 5. Okay, let me clarify that is, if you line up a row that you pick one card from the 25 cards, I think you will not put it back. So when you choose one, you cannot use this card again. So the second item is right, but there is something wrong with the first item. So the first item should be 15 2 permute 5 minus. Yeah, this one means that this means the all possibility that you can choose the five cards, and then you need to subscribe the possibility that all of them are black cards. Yeah. So the answer is this one, and I will not do the following mathematics to get the final answers, but the main idea is that. Now let's go to problem C. We have 4 suits in total. Okay, thanks for the answer. Now the answer is P13, 5. I think that means that because we have 4 suits and in each suit there are 13 cards, and then you need to choose 5 of them. But there is a small mistake in here, so can you think about it? Because we have 4 suits. Now the answer P13, 5 means that if once you choose one suit, then you can pick 5 cards from this suit. Yes, so we need to times 4 because there are four choices for the suit. Okay, any questions so far? If no, let's go to the problem D. Okay, there's a problem. Would it just be P265 since each suit is one color? Yeah. It can be black suit. So I will say Peter's idea is exactly what we want. So we want to add together the total number of lineups that have the same suit and the total number of lineups that are red. And then we need to minus that they are both red and in the same suit, because the first 2 items overcount the possibility that they are red and are in the same suit. So the final answer should be, this is what we have already get, that they are in the same, the number of lineups that they are in the same suit. And then this is the number of lineups that the fine cards are all red. And then because we have 2 suits that are red and they counted both in, they counted ones in here and then counted ones in the second item. So we need to minus this one half overcount. And then the final answer is plus 2 times 5. Okay, any questions so far? Now let's go to this one. Actually, this one is the hardest one, and you need to use the back problem again. So here is a hint. We need to use a theorem 3 in page 413. Theorem 3. The number of solutions to x1 plus x2 plus xn equal to r using non-negative integer Okay, this problem is a little difficult, so I will give you another hint. Another hint is that we needed to rewrite the requirement of this problem in a more mathematical way. So we can let x1, x2, x3, x4 to be the values of vertices. So we want to know the number of positive integer solution for the equation x1 plus x2 plus x3 plus x4 is equal to 12, and xi is larger or equal to 1, and xi is larger or equal to 1, and it is smaller or equal to 6. Yeah, and I see y answers from a plus b plus c plus d is equal to 8. That is a very good point. That means we can divide it into two cases. The first case is the number n. The number n is the number of positive integer solution for x1 plus x2 plus x3 plus x4 is equal to 12. And n2 is the number of positive integer solution that x1, x2 plus x3 plus x4 is equal to 12, and at least one fi is larger or equal to 7. So the final answer would be n1 minus n2. So we need to define the answer for n1 and define the answer for n2. n1 is that we need the number of solutions that's all the positive integer. But if we want to use theorem 3, in theorem 3, we use it as non-negative integer. But we can think about it in another way. That is, we can minus 1 for each item. And then the right-hand side should be minus 4. And then each item would be a non-negative integer, because this in here, if x1 minus, because x1 minus 1 could be equal to 0. So we will say n1 is equal to the number of non-negative integer solution of x1 plus x2 plus x3 plus x4 is equal to 8. So this is we also see a plus b plus c plus d is equal to 8. I think the students use the same idea. So that means then because this is an equation and the solution is non-negative integer, so we can use the theorem 3 directly. That is 8 plus 4 minus 1 plus is equal to 11, choose 8. Any questions so far? So let's get a review of this question. So the original one is that x1, x2 plus x3 plus x4 is equal to 12. But in this solution, we require it to be positive integer. So we can minus 1 to each item, and then the right-hand side becomes to 8. Then this item become the negative. Then we can use theorem 3 directly. Okay, let's go to the N2. In N2, we want to find x1 plus x2 plus x3 plus x4 equal to 12. And at least one of them is larger or equal to 7. And because we need it to be non-negative, so we can do the same magic. We can minus 1 to each item. Then this is minus 4, then that's minus 1, then that's minus 6. So we have N2 is equal to the number of non-negative integers solution for x1 plus x2 plus x3 plus x4 is equal to 8, and at least one of the AI is larger or equal to 6. So there's a number. We can, there is a question about the N. So in here we see the N is the number of the items. So in this one, N is equal to 4. And R is the right-hand side. So R is equal to 8. I hope this makes sense. Okay, let's continue. So we get here, but we cannot use theorem 3 directly because we also have a condition. But think about that, we can only pick one item that is larger than 6. Because if we choose 2 items that is larger than 6, then the other 2 will be negative. So we have 4 ways to choose xi that is larger or equal to 6. And then if we minus 6 in both sides, and the right-hand side becomes 6. And this one, no matter which xi you choose, you can, for example, you choose it to x1. x1 is larger or equal to 6. Then This 4 item is still non-negative. So we have N2 is equal to the number of non-negative integer. For the solution, x1 plus x2 plus x3 plus x4 is equal to 2. We get it from here. And then it is C 4 plus 2 minus 1 choose 2. It is equal to 5 choose 2. So the final answer n is n1 minus n2. It is equal to 11 choose 8 minus 5 choose 2. So this is the final answer. Okay, I'm running out of time. So if you have any other questions, please go to our office hour. And my office hour is just 3 minutes left, 3 minutes after. So if you have any questions, please go to my office hour directly. Thanks for coming. Then let's end for today.